Good morning, good afternoon, or good evening, depending on when you are watching us. And thank you for being part of the Material Business Podcast and being here with us. Today, I have a really special guest. Florent, thank you so much for being with us today.
Thank you for having me.
So, Florent graduated with a master's in materials engineering from Estienne, now is the Polytech Nancy in France, and a PhD in material science from the Imperial College in London, UK in 2005. He worked as a postdoctoral assistant and as a research scientist for 4 years at the Center for Electrochemical Science and Engineering at the University of Virginia. He has been at the Southwest Research Institute, San Antonio, Texas since 2009. He's been involved in different aspects of corrosion research and development during his career, from studying the corrosion properties of novel aluminum, I don't know how to say that word anymore, for wing skin, to evaluating materials for high temperature and pressure turbine applications. His original focus was on hands-on experimental work, but he has expanded his interest using environmental modeling tools, development of high-pressure, high-temperature test facilities, and improvement of large corrosion data collection and storage. For over 5 years, the focus of his work has shifted to supporting the corrosion needs in transitioning towards more sustainable technologies. Florent, it's impressive and it's very interesting to see in how many different areas you were able to work and how it evolved kind of in your career, all these aspects. When I reached out to you, it was a very cool article that had a very cool name. And I said, I want to talk to you about that. And I want the audience to talk to you about that. Can you tell us a little bit about that project and what is being that modeling for the environment on Saturn moon? Listen to that, guys. Saturn moon. We are not talking about that. Anything boring here. And how those tools can be compared to what we do here to analyze corrosion.
Yeah. So the best way to start to explain that is a little bit of a story time on how I ended up getting involved with that type of work. So working at Southwest Research Institute, there is a lot of people who do a lot of things, and including some work on space science. And through different internal meeting, I ended up connecting with somebody in our space science group called Charity Phillips Lander. And she has been doing some work funded by NASA to look at the impact of organics and different ions on the freezing temperature and the phases present in ice that are expected to be found on those ice cap of ocean world. And Enceladus is one example, Europa is another example. At the same time, for years and years, I've been supporting our corrosion group with thermodynamic modeling software. And the way I use it is to actually model the environments that we're testing. So sometimes it can be really hot environment inside an autoclave, high pressure, high temperature. We can't really measure the pH in there. But using these tools, we can actually back calculate what would be the pH at ambient pressure and ambient temperature, where we can actually measure that. And so talking with Charity, what I realized was, well, the same type of tools could be used, except with very low pressure, temperature, but to potentially look at the environment that she was looking at. So we got to talk about that. She was really interested in discussing this because there are limitations to the tools that are being used by the space science community. One of the limitations was to actually include organics. So they were able to model things with sodium chloride, with potassium chloride, all of this in there. But organics was a huge barrier that they weren't able to cross. So I just turned on my laptop and put on the software and asked her, okay, send me the list of what you're working with. I'm going to see what I can do with that. And so I realized that there is a bunch of organics that were in the software. After that, I also talked with the provider from the software, and they told me that actually they do have integrated in there some extrapolation of temperature to go to very low temperature. We're talking minus 50 degrees Celsius at least. And the reason why they do have some of the organics in there is because they do have some data, thermophysical data on organics. So after that, running some calculation, I got back with Charity and we talked about what I was finding versus what she was seeing in the lab. And some of the effect of organics that I was seeing in my calculations was actually what she was seeing in the lab. And, that was really interesting because it's a software that I primarily use for oil and gas application. But it is a tool that can transition to help resolve other problems. And looking at it at a much higher level, at the end of the day, when we work with corrosion, it is the interaction of materials with the environment. And using this software is looking mostly at the environment. And the way what they are trying to solve on these planets, on these moons, is an environmental questions. And so it actually kind of makes sense that potentially that expertise, that knowledge that we get can transition to that. And so right now what we are doing, we presented some of those results. There was some pretty good response to it in front of the space science community. There was some pretty good response to it. And our next step is to try to actually get some funded work with a goal to actually improve the modeling of those organics, because we know, and the vendor of the software also is very much aware of that there are limitations to what we can do with that software, but there are ways to make things better. And so the end goal is figuring out whether we can model the environment in a way where we can prove that there are some of the phases, so at low temperature having some bubbles, basically some vapor bubbles inside the ice, where life could potentially exist. And so they're doing correlation with some of what they're finding in Greenland, for example, where they do studying the ice over there and looking at the presence of bacteria and so on. So, yeah, on paper, it looks like it's a huge leap to go from corrosion to supporting finding of life in space. But looking at the expertise and knowledge and tools being used, it is actually not that big of a leap.
Wow, it's so amazing. And I know probably Alec Broisman. He looks at corrosion from every aspect, music and politics, and not only materials. But now you're talking about an extra level, is like, how can we support a field that in our mind will be so different, so completely out there, and it is possible by using tools that we use in our day to day. So it is amazing. The power of collaboration, I guess.
Absolutely. I think that if we're looking at the problem of corrosion, and that's a little bit of going on a sidetrack here, but looking at a lot of the problem of corrosion in the world, we are really a passenger in a lot of those technology problems, whether we're talking about development of a bridge or development of a plane or a pipeline or whatever. At the end of the day, corrosion usually is not the primary problems that needs to be solved. It is not, nobody builds a pipeline to solve corrosion. And so we are here quite often as corrosion engineer and scientists as a support to make sure that things are actually going well. And in this case, it's taking the same approach. It's being there as a support to that team while looking for potential environment that can support life to help them answer some of those questions.
It is very amazing that we are able to find those links and then help other scientists accomplish things. It is amazing. So you've also been involved a lot, and we said that when we did the introduction on sustainability and sustainability projects. Could you expand a little bit on the significance of the term sustainability? I know this is a la mode right now. We just finished COP28. There were a bunch of things that were there, but like really for us, materials corrosion. Like, what can you tell us about it?
Mm-hmm. So again, I'm going to start with a little bit of a story. I just always think that it's a little bit more interesting that way.
I love stories, and it's really...
So now it's been nearly 7 years ago. A colleague of mine from Southwest Research Institute named Erika Maka, who I've met her when she was doing a master at the University of Virginia. I was a postdoc, and years later, she started to work at Southwest Research Institute. And so every now and then we were having lunch together. And at some point, about 7 years ago, during those lunches, we started to talk about what we wanted to do in terms of, what problems do we want to solve? What do we want to be involved in? At the end of the day, I think a lot of us who end up going to grad school, it is because we want to be involved in big problem. We dedicate that time earlier on in our career to be able to actually do something we love and we want to do. So we are talking about this, and we really agreed on this question of climate change. We need to do something. What can we do as corrosion engineers? And starting from there was a lot of conversation because, we're corrosion engineers. It's, even though we do have the same expertise on paper as people develop batteries, in a way, it's not really a forte. We deal with accidental, detrimental electrochemistry. They deal with controlled electrochemistry. So it's kind of different. We live in chaos. They live in controlled power in a way. And so we were going through a lot of these and renewable energy, and we also went through some of the conversation about, what is sustainability, what is all of that. And I feel like I still see very regularly those conversations about in the corrosion community about, let's define what sustainability is. Having worked in a lot of different projects related to sustainability, I think that people kind of have an idea of what it means. It doesn't need to be defined. It's just too complex to be defined. We can spend, I think within the corrosion community, we could spend 2-3 years on trying to define what is sustainability for us. But that's not what we should do. We should work on actually, again, supporting the corrosion problems of technologies that are solving this. And we're wasting time in trying to really put the term sustainability in a box. I think we just need to accept the fact that roughly it is now kind of solving the problem of climate change by making things better and not destroying as much. And that's kind of the general idea. And there are different technologies that deal with that. Some of them people think that it's not actually sustainability, like carbon capture. It's not. Some people are actually starting to get really against that. in my mind, it's still within the sustainability because it still helps to solve that problem. But in a shorter sentence answer, I don't think we need to care that much about what is sustainability. We just need to deal with it. We all have a general understanding of what it is, and I think that's good enough to work on the technologies to solve it, to reach it.
It is great what you're saying. Sometimes we get so tangled into the details because we are engineers, you know. Yeah. And then if we do what we're supposed to do, like if we manage assets, if we control corrosion with anything that we have right now in hands without going and do something extra, we've already reduced the amount of consequence that corrosion is causing. So we'll just I love what you said. Is we just need to work with what we have, make it happen, regardless of the definition per se.
And with some of the work that I've been doing, supporting folks who are developing new ways to create energy, especially using machinery, quite often what I've realized is quite often to actually help those cleaner technologies to work, or to make some even existing technologies more efficient and reduce the amount of greenhouse gas being released, we need materials that just work better at high pressure, high temperature. And one of my colleagues once told me, if it wasn't for you material folks, we would be able to do great things. And, in a way, within that area of machinery, energy production, what we need to do is already been established. We need to actually be able not only to make materials that are able to handle higher pressure, higher temperature, from a mechanical point of view, from an oxidation, degradation point of view, and we need to make sure that they're reliable. And that's a huge problem. But again, I think that we don't need to spend time on talking about what is sustainability from the point of view of corrosion when there is that gigantic problem that is already there. And, for some of it, we don't even have the ways to test those materials at those conditions. And so there are a lot of things that can already be done.
Exactly. Yeah, sometimes we're looking for problems where we have the problem in front of us. So you need to solve it. If you want to solve it, sometimes the solution is already in hand. It's just improving the way it is done, managing it better. And then it will definitely. Excellent. So can you share some of the projects that you have been involved that perhaps help on that area?
Yeah. So like I was saying earlier on, one of the interesting aspects about working at Southwest Research Institute is that it's big. It's 3,000 people, and it is people working in a lot of different things. So people working on automotive, some people working on fuel, some people working on space science, on chemistry, some people working on things that I am not allowed to know. And so there is a lot of different type of work that is being done. And at one point earlier on, I decided, well, let's reach out to those people internally. It's just easier than trying to actually build an entire new network outside. And they're quite often more easily reached just by booking a 1-hour lunch together. So that's what I ended up doing. And I talked with some folks that are in fuel, lubricant, and automotive. And it turns out that when people are looking at electric vehicles, there are a lot of things that are changing. Some things that do not change. I mean, a tire is a tire. I'm sure that people who work on tire would be able to tell me actually it's not quite the same because you've got different torque and so on. But there are other aspects where corrosion could potentially be an issue. And so once you put an electrical engine in there, right there, you're changing the materials that you have. It's not going to be the same as an internal combustion engine. So, for example, you're potentially going to have a lot of copper. And also because some of the requirements, now you really need to take into consideration the power that goes through this copper. Some of the liquid that are there needs to be different. And, often when we think about liquids in a car, we're thinking about the fuel, we're thinking about the oil in the engine. And we could imagine, well, in an electric vehicle, you don't have an engine, you don't need oil, and you don't need gas. But you still have a lot of parts that are in motion, and so you'd still need a lot of lubricant. But those lubricants need to have slightly different parameters. You have different materials. And so some of the questions that exist there is, well, how do those materials behave with those new oil and new lubricant? And so that's some work that I've done. And that's actually interesting because those lubricant, those oil, quite often are not very conductive. So a lot of the tools that we have at our disposition, especially electrochemical techniques, they are becoming very difficult to use because of the very low conductivity. So there are ways to work on this, and we can either go back to the traditional way of using mass loss or looking at other techniques to be able to do that a little bit better, trying to play around with electrochemistry. But that was one of the programs that I've been involved in a few projects. Another one kind of related to automotive biofuel, when there is a lot of potential for corrosion to happen, for interaction with material. But what I've looked at is on the process side. So a refinery, we're talking about high pressure, we're talking about high temperature. The environment is very different from traditional refinery and actually quite more aggressive. And people are also looking at a lot of different product that can be refined to make a biofuel. So we're talking about whether it is waste or whether it is refining plastic or using soy and corn. And all of that just bring a lot of different complexity to the problem. So we've done some of that work, and we're still doing some of that work, evaluating some materials in those high pressure. So we're talking about over 1,000 psi. So over 1,000 psi. I have a table next to me just to remind me that's above 70 bar, and temperature going up to 450 C. And so that's we're pushing the ability of some of the tools that we have, but we've been able to do that. I've been doing also some work on the other end of the biofuel chain, looking at ethanol fuels and that are mixed with standard fuel, and working on both the corrosion of materials with this. So that's when they're in tanks, for example, on a truck or things like that. And working also on doing analysis with some of our colleagues here of the degradation of the fuel. So when it is at fairly high temperature, so 30, 40 degrees Celsius, how does it behave? How does it change over time? Because it will corrode with the materials, but can it actually change as well? How much water will it absorb? And so, yeah, the biofuel has been another thing I've worked on. One thing I've been really excited about, I was talking earlier on about energy production, is some work on supercritical CO2. So we have a pretty big group here that does machinery design and a lot of really exciting work, a lot of mechanical engineers. Um, I'm learning a lot on a lot of new things that I never thought about before. But anyway, about, I don't know, 12 years ago, 13 years ago, they started to do some work related to supercritical CO2 at high pressure, high temperature to create energy. So the idea behind it is replacing the thermal medium that you would have in a turbine with supercritical CO2. So, for example, you have a turbine that traditionally would have steam making it turn. You put supercritical CO2 instead of steam, and behind the idea is that you get a higher efficiency. You can have a much smaller turbine for the same power output. And so I had kind of the best project ever to start in a new area. One of my colleagues there, who's now the director, was working on a big project. They needed to do some material testing, and he asked me to basically do a literature review of what materials they could do based on their properties in supercritical CO2. So I got paid to actually read a bunch of articles and do a literature review, which is great. It's a great way to get in there. And so through the years, we developed a test facility to do some fairly low temperature pressurized supercritical CO2. So that was about 450 degrees C and just above supercriticality, so 1500 psi. And CO2 becomes supercritical at 1100 psi and at 32 degrees Celsius. So that allowed us to create some data, and we're doing that through internal research. But we're actually still using this setup now, which was kind of a crude setup, but we're still using it to test some materials, some magnets for magnet bearings. Another thing that's been really exciting is through working on smaller project with these folks, I got involved into a bigger DOE, Department of Energy project, with the goal to develop an oxy-combustion turbine. So the oxy-combustion turbine requires using supercritical CO2 with some other things in there and having it work similarly to a gas turbine. So there's going to be oxy-combustion in the turbine that makes the turbine turn. So it's different from a steam turbine. One of the big challenge from my point of view and from the materials is that they have a maximum temperature of 1150 degrees Celsius at 4,500 bars. So let's put that about 300 bar, 4,500 PSI, so about 300 bar. And I got involved into the project to do some material testing for that. If you've ever looked at ordering any type of high pressure, high temperature test vessel, they don't go anywhere close to that pressure and temperature. So we've been working on developing a system where the design is the concept is similar to a nuclear reactor. Instead of heating from the outside, having the entire vessel able to handle the pressure at test temperature, we put the heat zone on the inside and cool the outside. So we put an induction heater inside an autoclave while the autoclave is being cooled actively from the outside. So the autoclave itself is inside a water bath, which is a crazy idea. And it's been really difficult to do that. But we've been able to reach about 300 bar with the highest temperature we measure in there is about 1,000 degrees Celsius. The main problem is that the thermocouple we are using keep other work related to that. I think that we actually reached 2,000 degrees Celsius at pressure inside, which at this point is becoming interesting to going back to the space science community because it gets close to planetary formation temperature and pressure. So that's exciting because we're the only people in the world able to do this. It is really R&D. It's a lot of extremely complex problem to solve. My boss now told me the story that I can't remember his name, was running the Skunks lab, who apparently had this saying, only one miracle per project. I think in this project, I've asked for a little bit too many miracles to happen, but looks like it's going there. And so that's really exciting because it goes back to what I was saying earlier on. There are challenges that already exist. We don't have to care about what is the actual definition of sustainability. We already have enough to do right now. So yeah, that's kind of it. And I mean, there's been a few other stuff, working also on the carbon capture and, well, transport and sequestration, where we've got history in doing some of that, and we're working on getting more of that. There's been, like, it seems everybody, we're doing some work on hydrogen. However, early on, it's something I made the decision to not really get too involved in that, which may not be the smartest decision in my career based on how much money goes into hydrogen. But yeah, colleagues of mine were already doing it, and it was getting a little bit crowded, I didn't think, and I had quite the expertise needed to really improve things.
It's amazing. I was just listening to everything that you said. And if you would have been one of my, if I would have listened to you talking like you're talking right now when I was in university, I would have been like, oh my God, I am in the field that I need to be, And now I'm listening to you 20 years after I've been in this field, and I still think the same. So it is so inspirational, because the problems are always there. And then I have people said, oh, this field of corrosion has never evolved. And now listening to everything that you're saying, it's probably not the corrosion is evolving, but it's the kinds of problems that we get to solve, the kinds of challenges that we are able to contribute to. Those are the things that change. So yeah, the phenomena might not change. However, the way we act and what we do is what it is evolving.
Yeah, I think that it got a little bit more interesting for me once I've decided to accept the fact that I would probably never be the most important person in a room doing a meeting ever. Because, I mean, the goal of a plane is to fly. It's not to not corrode. The primary role of a plane is to fly. The primary role of a turbine is to produce energy. At the end of the day, as corrosion people, will help people achieve their goals, but we're probably never going to be the most important person in the room. And if we are, I think if we are the most important in the room and we want to solve problems, we probably shouldn't be in that room.
Definitely.
It took me years to try to gain enough to, I guess, be humble enough to stop trying to just lead things.
Yeah, that's a very interesting point of view. So we've seen the evolution until now. Where do you see this going forward? Like, how can we go? What is the next um, step in this realm? What do you think?
Oh, I think that there are two problems that have really been bugging me over the last few years, and unfortunately, they're actually not necessarily purely corrosion problem, but um, the first one is about communication. And years ago, when I was first starting to try to, when we were having those conversations with Erica about finding what we could do with climate change, I realized fundamentally the communication problem with climate change and corrosion is extremely similar. Basically, we're trying to convince somebody now to take an action on something that will happen in 10, 20 years. And if they are taking the action, they will not see the problem. And so it won't tell them that their action was successful. So that is one issue. And another one is most likely the person we try to convince now is somebody who will not be in a position where, if it does happen 20 years from now, they will be impacted by it. They may not even know it. And I think that it goes back to trying to be a little bit humble, is that if we enter a room and we have that person who made the decision, more than likely they probably won't know too much about corrosion. Our role as a corrosion expert is to make sure that somebody who does know very little about corrosion understand it and realize why it is a long-term problem that needs to be addressed now. And it is, I think, it is something that is starting to connect with psychology about communication of high-risk problems. And it was interesting. I actually reached out to a professor earlier this year who deals with that and has written some paper on psychology of risk communication related to climate change. And we were talking about that. And I was kind of glad to hear that she thought that the way I was talking about corrosion, there was a lot of similarities. And that, yes, there are ways to transmit that, and there are ways to make a big mess at trying to explain to people that corrosion is a problem. And I'm not entirely sure that as a community, we're doing the best that we could to get that that idea of corrosion being a big problem across to the people that actually make the decision. The people, somebody once told me, all you guys start your proposal and paper saying the cost of corrosion is 5% of the GDP every year, and 25% of it could be saved if proper corrosion management was done. It's a huge money. It's a huge number. And yet people are refusing to fund a 50K program. If that's that big of a problem, why don't they want to actually fund it? And I think that we can blame as much as we want the person who makes the decision, but it is our role to actually communicate that properly. And if they're not making the decision to fund this type of work, well, it is without doubt a big problem. I don't think it's on them. I think it's on us. It's us who are not doing a good job to explain that to them. Maybe we come into the room thinking we're just going to throw equations and that's going to work wonders. We're just going to throw some photos of a massless coupon and they're going to believe us. I mean, I don't think it has worked the best it could so far. So probably it's us that need to change that. So that's one thing.
Mm-hmm.
The other one is, like, everybody's talking now about artificial intelligence, neural network, about big data and all of that. And I think that we can see clearly at conferences that a lot of people want to do that within the Corrosion community. And I think that there are huge potential of using those techniques. However, I think that the main problem in the Corrosion community right now is not the development of those models. It's having the data required to make those models useful. And we cannot make a neural network or artificial intelligence work with 50 data points. We can't make it work with 100. We can't make it work with thousands of tens of thousands. When we're looking at some of those data sets that exist out there to train artificial intelligence, some of them have tens of millions of data points, and we don't have that type of data set that exists in the community. And even if we could potentially have them, there's just the beginning of an effort now to actually create them, because it needs to have data coming from a lot of different places. And it's actually kind of exciting to see that people are finally talking about that and coming to a realization that the data is needed and the data needs to be combined in order to get that. So I think with artificial intelligence, we are jumping to the results quite often and forgetting what is needed beforehand. And I think it goes back to also, what we're talking about right at the beginning. It's about collaboration. It's about working with folks that are out there. I mean, not everybody, but a lot of technologies can benefit talking with corrosion experts. But it also means that we need to go and talk to them.
Absolutely. And you're touching in 2 points that we have been saying, I think, in every podcast: collaboration and communication.
Mm-hmm.
And those seem to be very the root of many of the things that we could do better. So, Florent, we are at the end of the podcast. Thank you for your time. It's always fascinating and it goes so fast. And after I start listening to what you guys have to say, I always want to stand for 3 more hours. But thank you so much for being with the audience of Material Business, for sharing all that, all the knowledge and your work, amazing work. Thank you for being an ambassador. Thank you for coming and saying everything to our audience. Do you have anything, like a last closing sentence to people that are listening to us?
I think it goes back to, well, at least for me right now, it goes back to remaining humble with the expertise that we have. We shouldn't expect, just because corrosion is a problem, we shouldn't expect everybody to come to us. Having that type of knowledge and expertise means that if we really want to solve some of those problems, we should be the one going out there and reaching out to those people. Like I was saying, the first goal of a plane is to fly. And we have to make sure to tell those people that it would be great if it didn't corrode too quickly. So, yeah. Communicating humbly.
Oh, that's a really good closing sentence.
Yeah.
Communicating humbly.
Mm-hmm.
Florian, thank you again for your time, for your, abundance of information and inspiration for everyone that is listening. I look forward to having you again, maybe with some other more exciting things as they develop. And for everyone else, we'll see you in the next podcast episode. Stay tuned, and thank you for being part of the community of Material Business.
Thank you.